Hello there. My name is Leandro Chiarini. I'm a PhD student at IMPA. I'm about to defend my thesis. And today we'll be talking about one of the articles that is actually going to my thesis. It's a joint work with my supervisors, Professor Milton Hara at IMPA and Professor Violeta Russo at Utrecht University. And it's about quantifying central limit theorems for happy-tailed random walks. Before anything else, I would like to thank the organization of the event for letting me speak here. And well, I'm going to get into it now. So the objective of this article is to answer this question. What heavy-tailed random walks converge really fast, or like a very nice to approach a stable distribution? What I mean by that. So when we're working with probability models that are local in some sense, we tend to use the simple random walk to simulate something that is going to converge to the Brownian motion, right? This is the natural choice, not only because it has a bounded domain, it's very convenient and converges fast to the density of the Brownian motion in some sense. And so, yeah, this is very convenient for the case of normal distributions. It has all moments finite. It's a great distribution. But the question then is, what is the equivalent of the simple random walk in the case of non-local or heavy-tailed random walks, right? We aim to answer that. And to start, we're going to start with this distribution, P alpha, which is a power law distribution. Here, for now, we're talking about any dimension, but in a second, we're going to focus in the case of dimension d equal to 1. And if I have time, I might talk a bit about it, higher dimensions at the end. But what is nice about it is that the parameter alpha controls how many moments you have in this distribution, and therefore it actually controls in which Basin of attraction this random walk is. The random walk whose steps are sampled according to this law, right? And well, we know that such random walk, if proper normalized, here I'm talking about alpha, is smaller than 2. If they are properly randomized, this converges to some particular alpha stable distribution, which although we might not be able to write it explicitly for every value of alpha between 0 and 2, we still have this nice Fourier or characteristic function representation of the law, right? And our objective is to understand how fast I can get how good can be my bounds of the difference between the law of Pxn and the law of Pxn bar, where where x and bar is the random walk for which at each step you don't sample according to P alpha, but instead according to this stable law, right? And it might be useful to, before we start doing this, actually compare to what happens in the case that alpha is strictly bigger than 2. That is, we're in the Basin of attraction of a normal distribution. So a nice book that a nice reference for such kind of results, it's Lordler and Limmick's book, where they show that, well, here I'm really thinking of this bound as being an L infinity bound. They show that in this previous case, and they show that for every dimension, we can get this uniform bound to behave according to this exponent. And the exponent gets better and better depending on how many moments you assume that your distribution, the distribution of your steps have. So if you don't assume any further moment, that is, you only assume that it has enough moments to belong to the domain of attraction of the normal distribution, that is, I only assume 2 finite moments, my n to the minus d over 2 is the best that you can do. If you assume a third moment, you improve your rate of convergence a bit. And if you assume a fourth moment, you improve even better. And in fact, assuming further moments doesn't help you with the uniform bound. I don't know if we'll have time to get into why. But what is interesting to mention is that those values of beta are optimal in the sense that giving that a random walk that satisfies this, I can giving any rate here plus epsilon, sorry, I can get a random walk that that is converging up to this speed. So it's really optimal in this sense. And well, looking at this, looking at this list here, one might think, well, assuming further moments, so further integrability implies into like better convergence rates for the density of your random walk, right? But the question is, well, how do you do this for stable distributions, right? Because if I assume further moments, so if we're talking about our xn, whose steps, where x1 is sampled according to p alpha, x, assuming further moments would imply that it's not in the domain of attraction for the same distribution anymore. This wouldn't be in the domain of attraction for the same alpha anymore. So we need to think of a nice criteria for that. One could think about a coupling, but we prefer to have some less abstract criteria. And for us, it comes from this observation. In the proof that Lawler and Lamech provide, you can see actually that assuming moments, it's nothing but assuming some nice information about the characteristic function around zero, right? So in particular, suppose that you have moments of order 4 finite. And I don't know if I mentioned, but we're really restricting ourselves to the case of symmetric random walks for now. It's not necessary, otherwise you just have to ask some further information about moments of order 3. But to keep things simple, we have that this, now I'm really thinking about, from now on, I'm going to assume dimension z equals to 1. I have that the distribution of a random, the characteristic function of a random variable whose fourth moment is finite and bit symmetric satisfies this at theta equals to 0. And this is very natural because moments and expansion and the Taylor series of the characteristic functions go hand to hand together. But this is only true until the first moment, the first time that moment is infinite. After that, what happens is that this connection breaks. And possibly for our alpha, so for our alpha stable distribution, so random walks with parameter alpha, we can't do a Taylor expansion anymore, like in the same nice way, but instead you can do a further expansion that takes into account fractional moments. And this is precisely what we do. So instead of using Taylor polynomials, we try to compute explicitly the characteristic function of that p alpha that we did before. This is troublesome, and it's to be honest, it's a bit boring, but one can't compute explicitly the characteristic function of this random walk, and that's nice. And what it's interesting to compare also to this case of alpha bigger than 2, so in the domain of attraction, sorry, suppose that, yeah, so for those in the domain of attraction of a normal distribution, the bigger is the gap between this term here and whatever comes after that, so this error term, the smaller the error term is, the better the convergence rate is. So the smaller is the tail, the better the convergence rate is. And by tail, we mean anything that comes after the factor theta to the alpha. So in particular, it would be really nice if we could somehow get rid of this pesky theta to the squared term here. Because by doing this, by somehow getting rid of this, the convergence rates are actually much better, and we can explicitly estimate all of this. Right. So as this is positive, it turns out that we can actually make a distribution which we can do a random walk, or we can construct a random walk whose characteristic function is 1 minus kappa 2 theta squared plus theta to the fourth around theta. This is actually very easy. It just needs to, it can be a random walk which only assumes three values, 0, m, and minus m, and you just tune the probabilities and the values of m just right, so you construct this. And what is nice is that then if I multiply those two characteristic functions, I get rid of this term kappa 2 squared. So what I'm saying is that, well, that the random walk that we obtain by taking one step according to P alpha and then one step according to Z, like PZ, this random walk actually is going to converge much better than the random walk P alpha. And we call this process of getting rid of this parameter kappa 2 as repairing the random walk. Yes. So, okay, so for this kind of random walk, we actually proved for this result does hold for higher dimensions as well, but what we mean is that if you have a random walk whose characteristic function satisfies this, you actually get results that are as good as you would have the equivalent to the case in a fourth moment in the case of the normal distribution. That is, if we were working in dimension d, you could actually you could get this, which is d minus alpha plus alpha. And if you substitute alpha by 2, you see that it's comparable to the case of the normal distribution. Where again, P bar n is the random walk whose distribution, I forgot here, there is an n, factor of n here. Right, so each step, it's the random walk that at each step takes this stable distribution, right? And notice that this is actually only done in terms of the characteristic functions. This proof, it's actually very similar to Lawler and Lemmich's proof, as long as, yes, so for the uniform bound, the proof is very similar. As soon as you have those expansions, you can perform their same proof. However, they also have a non-uniform bound that gets better for Z going to infinity, which unfortunately we cannot reproduce here. We have other bounds that I'm not going to present here, but they're not as good. And this comes from the fact that they managed to show that P and X minus P and Bob X squared, this is equal to P O N to some power that to be honest, I forgot right now. But how they managed to get this x squared is to show that, again, writing in terms of the characteristic functions, I could then write this as 2 pi characteristic functions of the Laplacian of phi n e minus e theta x, the same part for the other one. But the thing is that the Laplacian has a very nice property of the product rule, where you can estimate things explicitly. To do the equivalent thing here, we would need to substitute this by the fractional Laplacian, which is a non-local operator. And the problem with the fractional Laplacian is that one of the problems with the fractional Laplacian is that it doesn't have a product rule. It only has an approximate version of the product rule. And unfortunately, this error of the approximate version diverges as n goes to infinity. So we cannot approach the same way. We have to do we have to do other techniques instead. So in particular, because we lost this non-uniform part, like the tail expansion, that it's a bit better, we have to approach the heat kernel that here we're only doing for alpha bigger than 1, but we can also do for alpha equals to 1, and we're thinking about how to do for alpha smaller than 1. But we can also estimate the heat kernel of that random walk, where again, I'm thinking of PZ, P alpha as the random walk. And what is nice is that before this result, as the best result I knew about the best results that we could find out about getting the expansion of AX, this is the heat kernel, were of just saying that this is of order X to the alpha minus 1. And here we manage this constant, it's explicit in terms of an integral, and we get some other term that is going to 0. Right. But what is interesting here is that we never used explicitly the fact that this was the distribution. So this is what motivates us to go to further distributions, like to really broaden this to a class. The class that we're going to think about then is what we call admissible random walk, or admissible random variable, which is a random variable whose characteristic function we can describe not in terms of a Taylor series or a Taylor polynomial, but we also allow for fractional powers here as well. And the fact that we have constructed, we show that P alpha belongs to this class, and that after correction we can even get rid of the kappa equals 2. We can show that we can any such expansion is possible. By this, I mean, like any such powers could really show up here. And what we do is that we manage to get those same results in terms of the speed of convergence of the random walk, and in terms of the error of the heat kernel. In terms of the characteristic functions, we managed to show like what are the terms after this main term here. Right. And yes, so this is not a silly class. This class is actually huge, and we can construct things of that. You should really think of this as what happened in terms of P alpha is that somehow, if you're trying to project the law of P alpha into the space of the laws of stable distributions. So it has, the first projection is going to be in terms of the alpha stable distribution, which is the limiting one, but it also has a term that it's of normal order, right? So it's of order kappa, oh sorry, theta squared. So it also has a normal distribution component. And this vision, also you can think of random walks which have several different stable distributions in the composition of this random walk. And we managed to really show that the bigger is the gap between the first term P alpha and the next term, we can actually show that these are the convergence rates, and also the bigger is this gap, the better going to be the error terms on the heat kernel. What is important to mention is that this notion is perfectly easy to, like perfectly natural to expand to any dimensions. However, showing that there are examples of them, it gets much trickier. The proof that of this proposition is already somewhat big, even in one dimension. We do expect to be able to show the same thing for small dimensions, but so far our argument is somewhat brute force. Yes. But one thing that is also useful to notice is that although this goes perfectly well for the local CLTs, for the green function or heat kernel, it's slightly different. For higher dimensions, the first term here would be substituted by alpha minus d. And notice that the second term, this error term, is always lower order. And this comes from our approach, which we try to write somehow this remainder as the Fourier transform of a smooth function. And because of those technical problems with the fractional Laplacian, we can only estimate so much of the smoothness of this. So we don't know yet how to do this for higher dimensions. Yes, the generalizations of those theorems and comments on other cases are all in our preprint. So those are the references, and thank you very much.